So first I'm going to give you a little introduction about GEMA itself. GEMA is the world's longest established provider of gem and jewellery education. We started teaching gemmology more than 110 years ago, prompted by the need for greater gem knowledge in the UK jewellery trade. Our early founders and distinguished presidents were trailblazers in the gemmological world and were instrumental in making their knowledge accessible to the jewellery sector. While the gems and jewellery industry is an ancient trade, the equipment and techniques developed by the likes of Dr. Herbert Smith, Sir William and Sir Lawrence Bragg and Basil Anderson enabled jewellers to look inside gemstones. These early years marked the first advances in practical gemmology, and the association was born out of a need for gemmological education for the jewellery industry, an ethos that continues to define us to this day. Since the first gemmological diploma in 1913, our association has grown into an international community of gemmologists, working with and for the wider industry. Today, our gemmology and diamond diplomas are taught in multiple languages in 26 countries across the world. Mindful of these roots, our courses are primarily tailored at the jewellery industry, giving you the background knowledge and practical experience you need in your career. You can learn about coloured gems and diamonds, their identification, value factors, and the many challenges of treatments and imitations, all crucial knowledge for buyers, sellers, and valuers of gems, as well as gem collectors, who are attracted by the extraordinary beauty of gemstones simply to wish to pursue a new hobby. So, what is gemmology? Humans have been fascinated with gemstones for thousands of years. They're among the rarest and most desirable minerals on the earth. History is intertwined with gems, with the latter playing important roles in economics, politics, religion, law, and fashion. We collect and possess gems for many reasons: to adorn ourselves or our surroundings, to demonstrate wealth, as investments, or to benefit from their supposed healing properties. Gemmologists, those who are trained in the science of gem materials, are like detectives. They identify gemstones and determine their nature, whether they are natural, treated, or synthetic. Accurate identification is essential to both the jewellery trade and the collector, and students who delve into gemmology find themselves in an exciting new world of observation and investigation into beauty and science. So, what we will cover today, during this webinar, we'll explain how diamonds are formed and why they are such a special gemstone. Their properties really are unique, and they are one of the most highly prized, valued, and widely studied minerals. We will also look at the 4 C's associated with diamond. These are the colour, clarity, cut, and carat weight of the diamond. These factors are how we assess the diamond and apportion a value to each stone. There are, of course, many factors that go into valuing diamonds, and we can only cover the basics in this webinar. The 4 C's are also listed within a diamond report, sometimes known as a certificate. These factors can help us identify the diamond. We will look at the basics of diamond reports and what to look for. We will also briefly discuss the main diamond simulants. A simulant can be any colourless stone that is used to imitate a diamond, but is not chemically the same material as diamond. The definition of a synthetic diamond, however, is that it is chemically and structurally identical to diamond. It is diamond, but it has been artificially grown in a laboratory. What we won't be covering in this webinar are any issues currently being debated in the diamond trade, such as the ethics of diamond mining or any opinions of natural versus synthetic diamonds. This is an image of a natural diamond crystal in its host rock called kimberlite. It's an igneous rock named after Kimberley in South Africa, where the first diamonds in kimberlite were discovered. There are 2 distinct types of host rock that contain diamonds: kimberlite and lamproite, and while they have a lot of similarities, they also have distinct differences as well. This image shows the typical octahedral habit of a natural diamond crystal. It has the distinct markings on the outside of the crystal, which follow the direction of the atomic bonding within the crystal structure. You can also see from this image that the crystal is of a very high colour, meaning that it is colourless or almost colourless. It also appears to be very free from inclusions. This is a really beautiful example of a natural diamond in its host rock. So before we go into detail about diamond formation, we need to understand the structure of the Earth. Our planet's structure comprises of the crust, the mantle, and the core. The crust is essentially the surface of the Earth where we live and where all our gemstones, including diamonds, are found. This is the thinnest part of the Earth's regions at around 40 kilometres thick, although this does vary depending on the age of the landmass and whether it is under the oceanic crust or the continental crust. To put this into perspective, the whole Earth is 12,700 kilometres in diameter. The crust is divided into zones known as tectonic plates that are constantly moving over the surface of the planet. They're pulling apart, pushing together, and sliding under one another, forming geological processes such as earthquakes and volcanoes. It is the volcanic eruptions that brought diamonds to the surface of the crust millions of years ago. The mantle, which is just beneath the crust, consists of mainly molten rock, and it is here where diamonds actually form. The core is at the centre of the planet and has two areas, the inner core, which is largely solid, and the outer core, which is largely molten. This diagram shows a more detailed look at the mantle. The place where diamonds form is known as the geological origin of diamonds. This is where they actually grow. There are a range of temperatures and pressures in the mantle, and diamonds mainly form under pressures of 50 kilobars at depths of 150 kilometres on average. A kilobar is 1,000 times atmospheric pressure, so the pressures that diamonds form at are 50,000 times that of atmospheric pressure. The temperature increases the further down into the mantle we go. However, this temperature varies depending on where you are in the mantle in relation to the crust. Below the thinner oceanic crust, at 150 kilometres down, the temperature is around 1,500 degrees Celsius. Underneath the thicker area of the continental crust, known as a craton, the temperature is slightly lower, at around 1,100 degrees centigrade. It is under these cratons, at the slightly lower temperatures, that diamonds have the right environment in which to form. So having taken into account the structure of the Earth, it is clear we now have a recipe for the creation of diamonds. One of the reasons that diamonds are so rare is that they require such specific circumstances to form. They need a temperature between 1,000 to 1,300 degrees and pressure of between 45 to 60 kilobars. These conditions are found at depths of 135 to 180 kilometres within the mantle, and they are only found under cratons, which we will define in a moment. They also need a carbon-rich environment. Without carbon, diamonds would not form, as they are predominantly made of that single element. If all these conditions are met, there will be an ideal environment for the formation of diamonds. If only one of these criteria are not met, then the diamond will not form and the carbon will bond differently or with other elements and form different minerals. In the upper mantle, carbon is believed to make up only a very small fraction of 1% of this layer, but additional carbon is constantly recycled from the surface of the Earth due to the subduction of the oceanic crust. So cratons are the oldest, thickest areas of the crust. The word comes from the Greek kratos, meaning strength. These areas have been folded, heated, stretched, and crushed by the Earth's geological activities for millions of years. These cratons were formed far, far back in geological time, and we know through scientific research and analysis that the approximate age of these areas, they are now left as thick, tough, rigid landmasses and are unaffected by current geological movement. If we look at this map of the continents, these cratons are further subdivided into archons, shown in green, These are greater than 2.5 billion years old. Protons are 1.6 billion years to 2.5 billion years old, and they're shown in red. Finally, tectons are the youngest areas of cratons, shown in orange, and these areas are 800 million to 1.6 billion years old. The pressure and temperature conditions that are required for the formation of diamonds are under the oldest cratons, the archons and the protons. If you look at where the cratons are formed on this map, you can see that geographically they coincide with the biggest diamond producing countries in the world, such as South Africa, Botswana, Australia, Canada, and Russia. So now we know the very precise set of conditions that allow diamonds to form. We're starting to build up a picture of why they are so special. In this part of the webinar, we're going to take a look at some of the other reasons that make diamonds special and cover some history and folklore, their age, their unique hardness. Diamonds are the hardest natural material on the planet. We will also explain the unique set of properties diamonds have that makes them sparkle. We will cover how diamonds are useful to us in ways other than decoration in jewellery as well. Diamonds were first discovered in India thousands of years ago, which was the principal source for diamonds until the 1720s, when diamond deposits were first discovered in Brazil. Ancient Hindu lapidaries believed that when wearing a diamond, it must be free of flaws, or else it would bring the wearer bad luck. Additionally, diamonds were believed to have the ability to protect the wearer from harm and render them courageous and fearless. Medieval authors in the West also believed that diamonds could protect you from being poisoned. So diamonds are a really handy gemstone to have around. They could instill courage and prevent you from being poisoned. Of course, the biggest association we have with diamonds today is with love. The majority of diamond engagement rings these days contain a diamond, and they're closely associated with phrases like diamonds are forever and diamonds are a girl's best friend, due to 20th century marketing campaigns by De Beers and movies such as Gentlemen Prefer Blondes, starring Marilyn Monroe. The first known diamond engagement ring is believed to have been given by Archduke Maximilian of Austria. He proposed to Mary of Burgundy in 1477. The ring had an inscription that reads, "My love will run out at the hoop's end," which of course it doesn't. Although according to some sources, the diamond itself was actually given as a dowry to her father. The ring isn't pictured here, but this is how it may have looked. Many early rings were set with diamonds that were uncut, leaving the actual stone in their natural octahedral pointed form. There are many, many famous diamonds, but some of the most well-known are the Cullinan, also known as the Star of Africa, and the Hope diamond. Discovered in 1905 in the Premier mine in South Africa, the Cullinan diamond is the largest diamond ever found, weighing in at 3,106 carats. It was cut into 9 major stones and 96 smaller stones. The largest stone cut from the original rough is 530.20 carats and is set in the Imperial Sceptre in the British Crown Jewels. The second largest stone, which is a square cushion cut, weighing in at 317.40 carats, is also in the Crown Jewels, set in the Imperial State Crown. Another diamond that's steeped in history is the Hope diamond, which is a fancy dark greyish blue, but we'll just call it blue for simplicity's sake. It is allegedly cursed, having caused great misfortune to those who have not only owned it, but to some who have merely touched it. It was purchased by the heiress Evelyn Walsh McLean, whose son and daughter both died. Her husband left her. She had to sell the Washington Post newspaper and died in debt. The diamond was later sold to Harry Winston, who donated it to the National Museum of Natural History in Washington, D.C., where it still resides. It is said that the postman who delivered the stone was in a terrible truck accident in which his leg was crushed, and he also suffered a head injury in a separate occasion. Diamonds are around 4 billion years old, which is truly ancient. To put it into context, the Earth itself is 4.5 billion years old, so diamonds have been around for most of the Earth's history. They were formed when the Earth was in a state of flux and can contain information to the history of the Earth's formation in the form of inclusions. The oldest known mineral on the Earth is zircon, which is a beautiful gemstone in its own right. However, the colourless variety of zircon has been used as a simulant of diamonds since ancient times. Some zircons from Australia have been dated at nearly 4.4 billion years old. Diamonds have been found with zircon inclusions. This can happen because, like any other growing mineral, diamond can retain impurities from its surrounding growth environment. These impurities can be single atoms of another element or complete minerals such as zircon. These inclusions are known as syngenetic when they form at the same time as the diamond that encloses them. Now we move on to the hardness of diamond. Diamond is the hardest known material on the Earth, and gemmologists measure hardness on a scale that is named after the German mineralogist Friedrich Mohs, who developed the scale in 1812. Mohs' scale ranks various well-known minerals from the Earth in a relative scale of hardness from softest to hardest. The scale increases exponentially as it goes from 1 to 10. Diamond is rated a 10 on the Mohs scale, and to put this into perspective, diamonds are 140 times harder than corundum, which includes sapphires and rubies. These are rated a 9 on the scale. The only natural material that can cut diamonds are other diamonds, and this quality has led them to being believed to be unbreakable. Please do not believe that diamonds are indestructible. They do have certain planes of weakness along which they can split when hit hard enough. This property is known as cleavage. Your jewellery should always be kept in boxes and pouches to prevent damage from gemstones and diamonds rubbing or knocking against each other for this very reason. Diamonds need to be cut to very specific proportions in order to display their optical properties known as fire and brilliance to the best advantage. The optimum cut for diamond is the round brilliant cut, which basically means when cut well, the round brilliant cut diamond is the most sparkly of all the cuts. The modern round brilliant cut was developed in 1919 by Marcel Tolkowski and was scientifically developed to exact proportions using the properties of diamond's refraction to return the light back to the eye in the form of brilliance, which comes from the table of the stone. The table is the flat surface in the middle. The fire, which is seen coming from the crown facets, the ones around the edge of the table, is seen when white light is split into its component spectral colours, like the colours of a rainbow that you can see with a glass prism. When they are cut well, diamonds exhibit a balance of both fire and brilliance. As you can see from this image, not all rough diamonds are beautifully clear and colourless and in a perfect octahedral form like the image we showed you at the beginning of the presentation. They can come in a variety of shapes, sizes, colours and surface textures. Anything that's not suitable for the jewellery trade can be used as industrial grit, used in cutting and polishing in a variety of tools used in dentistry, jewellery making or even mining. Diamond can also be used in medicine and technology. Because diamond is chemically inert, experiments have been made using nanodiamonds as cancer treatments and eye surgery implants. Diamonds are used in lasers, X-ray equipment and vacuum chambers for scientific experiments. Diamonds are now also replacing the use of silicon in computers, as they can get 5 times hotter and cool down quicker without sustaining any damage. Whatever it looks like, diamond is diamond, the hardest material we have, and every diamond can be used. Due to the exceptional properties and stability, the possibilities for use in science are endless. But back to the jewellery industry, where diamonds are most often seen. So now we're going to cover the 4 C's of diamonds. The carat weight. The weight of the stone is measured in carats, which is 1/5 of a gram. So 5 carats weighs 1 gram. It is believed that this weight measurement came about from the use of carob seeds in ancient times, which had a reasonably consistent weight of around 0.2 grams each, hence the word carat. In this webinar, we will not go into details about all of the fancy colours of diamond. We're just going to consider diamonds that are a shade of colourless. Diamonds are actually graded for their lack of colour under a specific daylight lamp. The reason for this is so that the same conditions can be met when colour grading all over the world where the lighting conditions might vary. Clarity grading means relative freedom from inclusions. Again, the higher clarity grades are the ones that are free of inclusions. All clarity grading is done under 10 times magnification, usually with a simple handheld loupe, but sometimes a microscope. The cut of the diamond can mean 2 things. The style of the cut is the overall shape, for example, round brilliant cut, pear-shaped modified brilliant cut, oval brilliant cut. The quality of the cut is also part of the grading process. And for this, we look at the symmetry of the facets and the proportions of the diamond. Each pile of rough, unpolished diamonds in this image equate to the same value, giving you an idea of the extent that size can have on the effect of the price of a polished stone. Diamonds are much rarer in large sizes. Therefore, the larger the diamond, the more expensive it will be, assuming that all of the factors such as the colour and clarity are the same. Every mine is different, but it can take up to 1,750 tonnes of rock to be mined to find just 1 carat of rough diamond. And that 1 carat might be a single perfect octahedral crystal that can be polished into the most beautiful flawless brilliant cut with a maximum price tag for the weight, or it might be a collection of industrial grit that totals 1 carat. This is another reason why we say diamonds are so rare, particularly in gem quality. Loose diamonds can easily be weighed on carat scales, and they are priced by weight. This chart demonstrates how the price moves up in steps at specific weights. This is due to the desirability of specific sizes, such as ½ carat weight and 1 carat weight. The pricing of diamonds is incredibly complicated, and the size is only one small part of the total calculation. It is due to the size and due to this that when designing the cut of a diamond from a rough crystal, that although factors such as the final expected colour and clarity of the finished stone are important, it is the maximum yield obtained from the original rough stone that is crucially important. Due to strict proportions for round brilliant cuts, estimation techniques can be used to calculate the approximate carat weight of diamonds set in mounts. This is necessary to estimate the weight of diamonds set in jewellery for valuation purposes, but this can only ever be an estimate. Estimation can also be done for fancy shapes, such as hearts, oval and marquee diamonds, but these are not quite as accurate. Diamonds are usually weighed to 3 decimal places and never rounded up, unless the final number is 9. Typical well-cut 1 carat round brilliant cut diamond measures 6.4 millimetres in diameter and 4 millimetres in total depth. So this is a colour grading chart. Diamonds can come in any colour. However, the majority of diamonds are graded for their lack of colour on a colourless to yellow scale. There are 3 different colour grading scales listed here. The Gemmological Institute of America, known as the GIA, CIBJO, which is the World Jewellery Confederation, whose headquarters are in Bern, Switzerland, and the American Gem Society. All these different grading systems are essentially the same, They all grade the colour of diamonds in the same way, to the same standard. They just use different terminology. So, for example, the GIA say that a diamond that is colourless, when viewed table up and table down, is a D colour, while Sibjo calls it exceptional white plus. The actual colour you see is the same. Most people start to perceive a change of colour at around H, but everyone's eyes are slightly different. Generally, the more colourless a stone, the more value it holds, unless we're discussing fancy colours where the opposite is true. More colour then equates a higher price. A fancy colour diamond is the terminology we use for a strong body colour of diamonds such as pink, green, yellow or blue. Colour grading fancy coloured diamonds is far too large a subject for us to cover today, so today we're just going to cover the colourless grading. Diamonds ranging in colour from near colourless to dark yellow are often referred to as the Cape series and form 98% of all mined gem quality diamonds. All the other fancy colours fall into the other 2%. In this image, you can clearly see the variety of yellowish colours that the colour grading scale refers to. This is, of course, much more difficult to see in the polished stones, which is why diamond grading needs to be done under laboratory conditions by an experienced diamond grader. The other most common tint is brown, and this is also graded on the same scale. This chart shows the clarity grading scales of both GIA and also Sibjo. Starting at flawless, remember clarity grading is only done under 10 times magnification. This means that a jeweller's loupe and the correct lighting, along with a trained eye, are all you need to clarity grade diamonds. The scale runs through to included, which is also known as PK, which sounds way nicer. At the lower end of this scale, you will clearly be able to see the inclusions without the aid of a loupe. Although the lower end of the clarity scale results in a lower price stone, when all of the factors are equal, included stones can be very interesting from a gemmological point of view. Imagine how special your diamond would be if it had a perfectly formed crystal inclusion of a garnet or a zircon inside it. So to recap, diamonds are graded for their lack of inclusions and are assessed with a 10 times loupe by an experienced grader. Brilliant cut stones have 57 or 58 facets, 33 on the crown, which is the top of the stone, and 24 on the pavilion, which is what we call the lower part of the stone. Some stones have an extra facet on the culae. The shape is qualified by the outline of the stone, for example, a round brilliant cut, oval brilliant cut, and paired brilliant cut, etc. Modern round brilliant cuts often have the highest price tag, as they exhibit a balance of fire and brilliance due to the reflection effects within the stone. Therefore, they are the most desirable cut. In addition to this, the sparkle from the brilliant cut can mask some of the smaller inclusions that might be in the stone. Step cuts have parallel facets to each other. One example of this is the emerald cut, which looks like a rectangle, but the corners have been removed so it has 8 sides. This cut was developed for emerald to better display body colour, hence the name, but it is also a popular cut for diamond. It was particularly desirable during the Art Deco period. However, with this style of cut, inclusions within can be easily seen as the fire is at a minimum. Old cuts are named purely because they were cut many years ago and have a brilliant style facet arrangement but without the correct proportions. They might not reflect the light in the scientifically perfect way, but they have a really special charm all of their own, and they look great in candlelight, which is what they originally cut for. Diamonds are also graded for the quality of the cut. This has a big impact on the way a stone can look, and cut is arguably the most important C of the 4 Cs and can affect the overall appearance of a stone the most. We discussed this a lot in more detail on our 5-day grading workshops and our diamond diploma. The symmetry relates to the facet arrangement and how well shaped they are. Due to the way a diamond reflects light, if the proportions are not ideal, this will result in a dull-looking, less sparkly stone. The proportions relate to the angles of the stone and need to be just right to reflect light correctly. The polish is the quality of the finish on the stone, and this can have a direct impact on the luster, which is a surface reflection effect, returning light that falls on a polished surface back to the eye. The diamond in the centre of this image is cut correctly and looks amazing with a balance of fire and brilliance. The one on the left is too shallow and it appears dull with the girdle reflecting into the stone. The one on the right is too deep, resulting in a dark patch in the centre. The cut of a diamond defines how well a stone interacts with light, producing both fire and brilliance, which is critical to the beauty and appeal of the stone. A well-cut, round, brilliant cut diamond can return up to 97% of all the light which enters the stone, which is why they look so bright. The quality of the cut is graded from excellent to poor, and this will be shown on your diamond report. Some of the factors that affect the symmetry of a diamond are the precision of the diamond shape. Is it really round, or is it slightly off-round, like this image? Is the table in the middle, or is it a bit lopsided? The culé is the point at the back of the stone where all the facets meet. If this is not quite in the middle, this can affect the symmetry grade. The widest part of a diamond where the crown meets the pavilion is known as the girdle. The girdle should be symmetrical, running evenly around the circumference of the diamond. If it's not, the symmetry of the stone can be marked down due to having a wavy girdle. If the facets do not meet properly in a nice, crisp point, this can also affect the symmetry of the stone. All of these factors are taken into consideration when assessing the symmetry of a diamond, and it's noted on your diamond report. These images show polishing lines. They're visible on the facets of a diamond. These occur during the polishing process, and this has been magnified many times, but the quality of the polish will affect how the diamond looks overall, and the quality of the surface is also graded and noted on the diamond report. This can also include blemishes such as abrasion and scratches. The girdle condition is also a factor that's noted on the report. So all of the factors we just covered go into the assessment of a diamond's price. This is a very complicated procedure, and the price of a diamond is affected by supply and demand, and ultimately desirability, so the price is constantly changing. There are price guides used in the industry to indicate the price of diamonds. These are tools used by retailers, diamond traders, and valuers, and require an annual subscription to the guides in order to access their data and information. Current market knowledge is essential to understanding how to use these guides, as they still need to be interpreted accurately for each individual stone being assessed. These are two examples, but there are many more that are used throughout the trade. Today, the majority of diamonds, particularly if they are of rare or large sizes, are sold with laboratory reports. A report provides an independent assessment of the stone, thereby providing protection for the consumer, and can also help you to identify the stone. The diamond report can be used also as a selling aid. However, the report should be carried out independently from the vendor. Diamonds must be loose for an accurate report to be carried out. Sometimes you will find reports issued for mounted stones. However, the colour and the clarity grades should always be shown as a range, not a single grade in this case, as it is not possible to accurately colour and clarity grade a mounted diamond. All the factors used for grading a diamond will be present on the diamond report. The colour, clarity, cut grade, proportion, symmetry, and fluorescence. There is often, but not always, a plan. It's like a little map showing where the inclusions and external features of the diamond are. This is really useful to check if the report does indeed match the diamond that you have. The measurements are also a good way to check the report matches your stone. Many more modern diamonds also have the report number laser inscribed on the girdle of the diamond. You should be able to see this with a 10 times jeweler's loupe. These are two examples of diamond reports. There are many other highly regarded laboratories within the trade. GIA has their own grading system, while SSEF uses the SIBJO guidelines. These are some of the things you can do to ensure that the report is genuine. Check the report was issued by a reputable independent laboratory with experienced gemmologists. Check for authenticity, such as anti-counterfeiting features such as holographic logos. And check the date. If the report was not recent, the stone may have been damaged, treated, or repolished since the report was originally written. As one of the most valuable and coveted gemstones in the world, it makes sense that diamonds have been imitated ever since their discovery. A diamond simulant can be as simple as a piece of glass cut to look like a gemstone, or as complex as a cubic zirconia which has been manufactured specifically to imitate diamond. A simulant is defined in gemmology as a material that possesses one or more optical properties of another gemstone. However, it may not possess the same physical or chemical properties. All the simulants listed here are able to be identified and separated from diamond with training and careful observation using a 10 times loupe. So to recap, a simulant is used to imitate another more expensive gemstone, often simply by the way of colour. Cubic zirconia is one of the most widely available diamond simulants. It was released in the 1970s, also simply known just as CZ. It's a completely artificial material, manufactured specifically to imitate diamond. It's grown in the cubic crystal system, the same as diamond, and made from zirconium oxide. It's not quite as hard as diamond, being 8.5 on the Mohs scale, and it's more dense than diamond. This is one of the ways cubic zirconia can be separated from diamond when it's unmounted, as it will be heavier than it looks. You can measure this by using something called specific gravity. This is covered further in the diamond diploma. There are also, though, many other ways you can tell if you have a CZ, not a diamond, such as rounded facet edges instead of the super sharp lines of a diamond, and the read-through test, which is pictured in this slide. Due to the optical properties of diamond, when well proportioned and placed table down over a line or a dot, you'll not be able to see through the stone. But with a CZ, you will see the line quite clearly. With training, identification can be undertaken with just a jeweler's loupe. You can also use a diamond tester to measure heat conductivity. Another widely used diamond simulant is made from synthetic moissanite, which is silicon carbide, which is a common abrasive material. Synthetic moissanite does have a natural counterpart, unlike cubic zirconia. The natural mineral counterpart is found in rocks that have been shock blasted by meteorite impact. However, these are tiny and not suitable for use as a gemstone, so there is no gem quality natural counterpart existing. Synthetic moissanite has very high dispersion, or fire, which can be seen from the crown facets as flashes of all the spectral colours. This is far more noticeable than in synthetic moissanite than in diamond. In addition to this, sometimes growth lines can be seen in synthetic moissanite, as can be seen in this image. They look like really fine hairs inside the stone, running usually from the table through the stone to the culé at the back, and they are very, very distinctive. You won't see these kind of inclusions in diamond. Another way that you can distinguish synthetic moissanite from diamond is by its double refraction. This is because it does not form in the cubic crystal system like diamond does. These two images show the difference when looking through the crown facets of a diamond and a synthetic moissanite. In the image on the left of diamond, the facet edges look very, very sharp and crisp, as you'd expect. However, in the image of the synthetic moissanite, the diamond looks fuzzy and hazy because the optical properties of the stone cause the edges of the facets to appear in duplicate. You'll never see this in diamond. Due to synthetic moissanite's hardness, it usually has a very good cut, very sharp facet edges and little to no damage with a sub-adamantine luster. Diamond has an adamantine luster, also usually with very sharp facet edges, so synthetic moissanite at first glance can look very convincing. So we've covered the main modern diamond simulants, but what about synthetic diamonds? Synthetic gemstones are laboratory-grown stones that do have a natural counterpart. So to clarify, these are artificially created stones that look and act most of the time like natural diamonds. When diamonds are grown in a lab, they are still technically diamonds, but they have not formed deep in the mantle in the earth millions of years ago. There are two main methods of manufacture, HPHT and CVD. These two processes do form crystals, but they look very different from natural diamond crystals. Today, most of the diamond grit used in industry is synthetic diamond. Synthetic diamonds of 3 carats and above have been produced, and the largest stone cut so far is 10.02 carats, grown by IGI in Hong Kong in 2015. This cut stone was fashioned originally from a 32.26 carat piece of rough. High pressure and high temperature synthetic diamonds are formed using immense pressures of between 50 and 80 kilobars and high temperatures between 1,350 and 1,600 degrees Celsius. Essentially, they mimic the way diamonds are formed in nature by providing the right ingredients for the diamond to form and the right kind of environment. Diamonds were first synthesized in 1954 and typically were an unnatural, strong yellow and orangey brown color, although this could be removed by further treatments to create colorless diamonds. A synthetic diamond still needs something to grow on, so seed crystals are used. These are tiny pieces of diamond that the carbon in the chamber can begin to bond onto. All types of diamond synthesis require a huge amount of energy to provide the high temperature and high pressures needed. The shape of the rough crystals are notably different to their natural counterparts, as you can see in this image. They grow predominantly in combined forms of octahedron and cube, known as truncated cubes or truncated octahedra. This image shows the different shapes of synthetic diamonds that have been grown using the chemical vapor deposition method of synthesis, known as CVD. This method involves the use of lower pressures and high temperatures to precipitate diamond out from gases within the chamber. The temperatures are between 700 and 1,300 degrees, and the orientation of the seed crystal gives a different crystal shape. The crystal grows layer by layer, atom by atom. These diamonds have a growth rate of 0.2 millimeters per hour. Although this is slower than the growth process with HPHT synthetic diamonds, the diamonds produced by CVD method are colorless crystals with a very high clarity. CVD synthetic diamond crystals only have one growth direction, upwards, and grow as tabular crystals, as can be seen in the image. They will take the same shape as the seed crystal or substrate that the carbon atoms are deposited onto. And some CVD diamonds can have small graphite inclusions, small clouds or pinpoints in the planes following the direction of growth. There are benefits to using this production method, as they are cheaper to produce than HPHT synthetic diamonds, and the equipment is small and costs less to run. Also, many diamonds can be grown at one time in one piece of CVD apparatus. Now, the seed capacity is reported to be possible to grow 50+ diamonds simultaneously in one chamber. This apparatus can also be used to form diamond coating and polycrystalline layers on various other materials. So to recap, diamond simulants can generally be identified using observation with a 10 times magnification of a loupe or a microscope. Quick indications are things like damage to facets, asymmetry of the facet arrangement, and a poor cut, as in CZ, and the doubling of the back facets that you can see in synthetic moissanite. Synthetic diamonds are much harder to identify. Technology has advanced so much in recent years that often the diamonds produced are of excellent colour and clarity. Using just a loupe with a diamond that is apparently a D colour, internally flawless, will not help to determine if it's natural or synthetic. You will need to use advanced laboratory equipment, and even then synthetic diamonds can be difficult to detect conclusively. There are many different pieces of equipment available to the trade and laboratories in order to help determine if a diamond is synthetic. They all work on different principles and require knowledge and experience to interpret the results correctly. Fluorescence is the general term used to describe emission of visible light by a substance whilst it is being illuminated by radiation of shorter wavelengths. Unlike natural diamonds, synthetics tend to fluoresce stronger in short wave than long wave ultraviolet light, as in the image. Approximately 20 to 30% of synthetic diamonds fluoresce. HPHT diamonds typically show a yellow fluorescence, whereas CVD diamonds typically show an orange fluorescence. Green fluorescence may also be seen in synthetics, although this is not a conclusive identification, just an indication, as yellow, orange and green fluorescence can also very rarely occur in natural diamonds. So I hope you've enjoyed listening to the webinar. The topics we've covered are only a small snippet of the full course covered in the Diamond Diploma here at GEMA. For more information about our courses in diamonds and gemmology, please check our website. There are many different ways in which you can study. You can study online with on-site lab classes, you can study at an accredited teaching centre, or at the GEMA headquarters in London, where we have both daytime and evening classes available.
Okay, great. Thank you so much, Delyth. That was really interesting. There was a lot of information there. It was really good. And thank you everyone for listening. I hope you all enjoyed. Right, so I think if Delyth still, do you want to do some questions? You have
Sure.
a bit of
We've got some questions.
yeah, so we have some questions to ask. First of all, how did you get into the jewellery industry?
Well, I've always been in the jewellery industry. I was interested in making things as a child, and I was always interested in gemstones as well. As a child, I was always picking up rocks and pebbles and things. When I left school, I didn't want to do A-levels, and I went straight to college where I learned to make jewellery, studying 3D design. And following that, I set up my own workshop, and I used to make jewellery in my own little workshop. And it was when I moved to London after 10 years of doing that I was introduced to GEMA and studied my Diamond Diploma first. I've worked in the jewellery trade for a number of years in a number of different roles now.
Oh, great. So you're very, very experienced.
Yeah, that's how I started.
Oh, great. That's really interesting. What would you say is your favourite diamond?
I quite like, I guess my favourite diamond has to be my own, my engagement ring. But I quite like optical effects. There is a diamond we haven't discussed here called, it's a type of diamond that actually changes colour according to either heat or temperature. It's called a chameleon diamond, and they're usually a shade of green or yellow. And and I'm quite interested in the optical effects of any gemstones, diamonds, and other gemstones as well. But yeah, chameleon diamond I think would be a favourite.
Wow, that sounds incredible.
But they are quite amazing to see.
Are they quite expensive, quite rare?
They are quite rare, and yes, they can, obviously, all of the things considered, yes. Size, colour, yeah, they can be quite expensive diamonds.
Oh, amazing.
Yeah, interesting.
This is an interesting one. So would you say you're a fan of synthetic diamonds?
Synthetic diamonds are here. The science behind them is amazing. I don't have a problem with anybody selling synthetic diamonds as long as the trade discloses to the consumer that they're a synthetic diamond, not a natural diamond. I think that's perfectly fair, and most, well, all good jewellers will have full disclosure of synthetic and natural. And also it gives a choice to the consumer. They can, you know, synthetic diamonds are cheaper than natural diamonds. So yeah, I am quite a fan really, especially with the technology.
Yeah.
I mean, they can be used in so many different places.
We'll just do one more. So what is the best instrument you would say to identify diamonds?
Well, let's not talk about synthetics now. Let's just talk about identifying a diamond. The best instrument, all you need is training, your eyes, and a 10x loop. There are also various instruments that can help you to test diamonds as well. There's thermal testers and electrical testers that you can use. They're more rather to identify diamonds, they're to identify what's not a diamond. But the best way to identify a diamond is just to know what you're looking for. So get the training and use a loop and your eyes.
But yes, thank you everyone for listening, and I hope you enjoyed. Right, thank you so much, Delyth.
You're welcome. Thank you.